Hey everybody, welcome back to Mr. A's geometry course. Today we're continuing section 7.3 using logic to prove that quadrilaterals are parallelograms. Today though we're going to be doing this on the coordinate plane, which is a little bit of a tougher task. We can use the 5 pieces of logic that we've learned to prove that shapes are parallelograms when they're graphed on a coordinate plane. Let's get into it. All right, before we dive into the methods we can use here on the coordinate plane to prove that shapes are parallelograms, it's important for us to remember the logic that we've already learned here in 7.3 to prove that shapes are parallelograms, because it's the same logic that we're going to be using on the coordinate planes. We're just going to have to do some math to prove that those theorems exist for our shapes. So as a reminder, we know a shape is a parallelogram by definition if opposite sides are parallel to each other. That is something we can prove with math when a shape is graphed on the coordinate plane. We learned about the opposite sides converse. If we know that opposite sides are congruent, then we know a shape is a parallelogram. Again, that's something we can prove on the coordinate plane. We know about the opposite angles converse. If opposite angles are congruent, then it's a parallelogram. That we're not going to be learning here in geometry, how to use that piece of information on a graph to prove that shapes are parallelograms. The only thing we're really going to be determining in geometry on a graph is if an angle is a right angle or not. If it's 90 degrees or not, we can find that out. Any other way of finding out angles would be extremely difficult for us to do here in geometry. Our next piece of logic is that diagonals bisect each other. If that happens, then the shape is a parallelogram. We can prove that on a graph with math. And then that last piece of logic, the one that most students struggle with, if one pair of sides is both congruent and parallel, then it's a parallelogram, and again, we can prove that with math. So there's a few different methods we could use to prove some of these theorems. The first one we're going to go over is the midpoint method, where we're going to be able to prove that diagonals bisect each other. All right, so we can use that diagonals converse on a graph to prove whether or not a shape is a parallelogram. So remember, diagonals bisect, that means they cut each other in half. And if something is cut in half, that point where it's cut in half at is the midpoint, right? So if a shape is a parallelogram, then the midpoint of one diagonal must also be the midpoint of the other diagonal. So if we can show that two diagonals have the same midpoint, then we will prove that the diagonals cut each other in half, and therefore our diagonals converse theorem would apply, and that shape would have to be a parallelogram. As a reminder, here is the midpoint formula. x1 plus x2 divided by 2, y1 plus y2 divided by 2. If you're here in the state of Florida, this formula is given to you on the reference sheet that you'll have when you take your end of course exam. So this does not technically have to be memorized, although it's not hard to memorize, and we should absolutely master how to use this formula. All right, so we're going to see how that works here. We have a figure on a graph, A, B, C, D. We are being asked to prove this is a parallelogram. And again, we're going to learn there's several ways to do that, but we're going to apply our midpoint method here. There exists here on this figure a diagonal from A to C and a diagonal from B to D. And if we can prove that those diagonals have the same exact midpoint, then that would mean this piece is congruent to this piece is congruent to this piece. The diagonals would be cutting each other in half, and therefore this shape would be a parallelogram. So let's see what that work looks like. So again, one of our diagonals here is diagonal AC. I'm going to stay organized. I'm going to write AC like this. I'm going to write the location of point A. It's at -7, +5. I'm going to write the location of point C. It's at +4, -2. The reason I write those out is so that I can label them and then carefully plug them into my midpoint formula. So x1, y1 for one point, x2, y2 for another. Those plug into my midpoint formula. x1, -7 plus x2, 4 divided by 2. The same thing with our y's. y1, 5 plus y2, -2 divided by 2. Then we do our order of operations here. That fraction, I have to take care of that stuff on the numerator. I got to do the -7 plus 4, which will give me -3. I got to do 5 plus -2 on the top right there, which will give me +3. And then I can divide from there, or I could leave them here as this fraction. It doesn't matter. I'm going to leave them as this fraction to show you that we don't have to divide fractions to write decimals down. We can just leave them there. So the x-coordinate is -3/2, the y-coordinate is +3/2. And we're going to do the same thing for our other diagonal here, BD. So again, what we've proved is that this is exactly halfway between A and C. If that same location is halfway between B and D, then that means where these diagonals intersect is the midpoint of both. And if it's exactly in the middle, that means that we would have two congruent halves. Our diagonals would be bisecting each other, making that shape a parallelogram. So let's look there for BD. Again, I'm going to stay organized. BD, I'm going to label my point B is at 6, 5. My point D is at -9, -2. One of them is x1, y1. The other point is x2, y2. And we're plugging into our midpoint formula. x1, 6 plus x2, -9 over 2. y1, 5 plus y2, -2 over 2. And we're adding. I'm going to move to the right here as I do this. So on my numerator up here, we have 6 plus -9. That gives me -3 over 2. And on my y side, we got 5 plus -2. That gives me 3 over 2. And look, the midpoints are the same. -3 over 2 for the x, +3 over 2 for the y. I've proved that my midpoints are the same on both diagonals, therefore the diagonals are bisecting each other, making this a parallelogram. All right, so because they have the same midpoint, right, we can say same midpoint, we can say diagonals converse. I'm just giving you kind of shorthand here of the ways that we can prove that this is a parallelogram, right? Sometimes certain teachers are want more than just math on the paper, right? They're going to want to know that what you did, proves that the shape is a parallelogram. They have the same midpoint, therefore the diagonals are bisecting each other. Diagonals converse tells us this shape is a parallelogram, right? So again, this is one method we can use to prove a shape is a parallelogram. If diagonals have the same midpoint, it's a parallelogram. The next math tool we can use to prove that a quadrilateral is a parallelogram on a coordinate plane is the slope formula. Why the slope formula? Well, slope formula obviously will give us the slope of things like the sides of a shape, which would be important to know because things that are parallel will always have the same slope. So we can determine if opposite sides are parallel by using the slope formula, and that would give us our definition of a parallelogram. A shape is a parallelogram if both pairs of opposite sides are parallel to each other. So we can prove that opposite sides are parallel to each other by showing with the slope formula that they have the same slope. Parallel things have the same slope. As a reminder, here's your slope formula. Lowercase m for slope equals y2 minus y1 over x2 minus x1. Again, this is given to you in the state of Florida on your reference sheet. You don't have to memorize it. You should though, it's an easy formula. We need to master how to use it. So as we look at this shape, notice it's the same one as our previous example. I'm just showing you there's another way you can prove this is a parallelogram. If you're more comfortable with the slope formula, we can do slope on all 4 sides of the shape. And the opposite sides would need to have the same slope. For example, my 2 highlighted sides right now, left and right, would have to have the same slope for this to be a parallelogram. So that's what I'm going to do. I'm going to find the slope of these sides and determine if they're parallel or not. So I'm going to start with side AD. I'm going to be organized. I'm going to write AD like that. Point A is located at -7, +5. Point D is located at -9, -2. And these guys are going into my slope formula after I label them. I almost forgot. Remember, labeling is very important. It can save you from making silly mistakes when you're entering coordinates into formulas. So y2 minus y1 on the top of our slope formula. So we got -2 minus 5 over x2 minus x1. We got -9 minus -7. -2 minus 5 gives us -7 up top. -9 minus -7 is the same thing as -9 plus 7, which give us -2 on the bottom. A negative divided by a negative is always positive. So we have 7 over 2 for the slope of AD. Again, for this to be a parallelogram, BC would need to have the same exact slope. So let's prove it. Again, staying organized, we have point B at 6, 5. That's x1, y1, and we have point C at +4, -2. That's x2, y2. That's a +4 there for that x2. Sorry for my handwriting. And again, plugging into my slope formula. y2 minus y1, I got -2 minus 5 up top. Then we have x2, 4 minus x1, that's 6. Negative 2 minus 5 is negative 7. 4 minus 6 is negative 2. A negative divided by a negative gives me positive. Look, I got the same slope. So I just proved AD is parallel to BC. Hopefully you got that, because I'm going to erase this now so I can keep the shape on the screen and show you that AB is also parallel to DC here. I have to prove it though with the slope formula. Like, this is not enough. What I just did, if that's all you do in a similar example, that's not enough. You won't get credit for that to prove that the shape is a parallelogram, because it's not just one pair of opposite sides parallel. They both have to be parallel for it to be a parallelogram. So now I'm going to do it on sides AB and DC. All right, so AB, and I'll tell you why we don't technically have to do this calculation for these sides in a moment. Just want to make sure that you guys get more practice here with their slope formula and understand the logic. A is at x1, y1, negative 7, positive 5. We'll say B is our 2's at 6, 5. We got x2, y2. And plugging into our slope formula, we got y2, 5, minus y1, 5, over x2, 6, minus x1, negative 7. 5 minus 5 is 0. 6 minus negative 7 is positive 13. 0 divided by anything is 0. And that should make sense because this segment AB is horizontal. It doesn't rise at all. And remember, we think of slope as rise over run. If the rise is 0, 0 divided by anything is 0. Notice the same thing happens with D and C. We don't rise at all from D to C. We're just going horizontal again. Therefore, the slope for DC will also be 0. Okay, so that means they have the same slope. They have to be parallel to each other. So we can say opposite sides are parallel. So by definition, this shape is a parallelogram. Again, by definition is saying opposite sides are parallel to each other. Right? So for me, if you're my student watching this, I want the work and I want you stating what that work proves. Those zeros, the slopes of 7 over 2 that we got for the left and right prove that our opposite sides are parallel. And then by definition, we now know that this is a parallelogram because opposite sides are parallel to each other. That's our slope method. The last math tool we can use to prove that a shape is a parallelogram on the coordinate plane is the distance formula. Remember, the distance formula is going to be used to figure out how far apart 2 points are, or to figure out how long a segment is, or a side of a shape on the coordinate plane. For example, as we look at this graph really quick, this side up here, I don't need the distance formula to figure out how long it is. I can just count it because it's horizontal. But remember, these diagonal segments like BC, I can use the distance formula on the endpoints to figure out how long that side is. Why is that useful? Well, because it tells us how long the sides are. And if we know how long the sides are, then we'll be able to know if opposite sides are congruent or not, which is one of the ways to prove that a shape is a parallelogram. So we can prove opposite sides are congruent by showing that they have the same length with the distance formula. And that would prove that our shape is a parallelogram. Right? If you're one of my students, the packet that I gave you, this formula said x1 minus x2. I just don't want to confuse you, because even though that's not technically wrong, the way that I've shown you earlier in the year is x2 minus x1 squared plus y2 minus y1 squared. Most places you look for the distance formula will be given to you this way. There is not technically a difference between the two ways. It's just a consistency that we've learned here to do 2 minus 1 and 2 minus 1 for our coordinates. Again, that formula is on the reference sheet. You don't have to memorize it. You have to know how to use it though. And we're going to use it in this figure. We're going to prove that the opposite sides are congruent in this shape to make it a parallelogram. Now again, side AB and side DC, we don't have to use the distance formula on those. We can just count them, all right? So AB, I can just count it, all right, with my finger straight across. So we're here at -7 going all the way to +6 on the x-axis. That is 13 units long. AB equals 13 units long. I'm gonna put that on the graph. DC, I can also count with my fingers from -9 here all the way to +4, 13 units long. I know those opposite sides are congruent, both 13 units long. I now have to prove that AD is congruent to BC. Those are diagonal, therefore we have to use the distance formula to figure out how long those sides are. I'm going to start with side AD. So point A is located at -7, +5. Point D is located at -9, -2. Again, I write those out so that I can label them, x1, y1, x2, y2, and then I can carefully plug those into the formula needed, which is the distance formula in this case. So x2, -9, minus x1, -7 squared, plus y2, -2, minus y1, +5 squared. Order of operations from here, we got to do the parentheses stuff first. So -9 minus -7 gives me -2. -2 minus 5 gives me -7. Next, I am doing my exponents, so I got to square those. -2 squared is +4, -7 squared is +49. Then I can add those. 4 plus 49 gives me the square root of 53, which I could do the square root of that and write around a decimal, but I'm not going to. I'm just going to keep it as this exact length in here. I know it's a square root of 53, and therefore if this is a parallelogram, BC would also need to be the square root of 53. So I can prove that by now also finding the length of that side with another distance formula. All right, so I'm going to erase what I have written down here already so that I can keep everything on screen for you guys. And we're going to do this now with side BC. So BC, obviously for you working at home, if you're doing this, you don't have to erase anything. You should have enough space to show when you work, or you can use paper with enough space on it to show your work for these examples to get it down. B, x1, y1, C, x2, y2. Doesn't really matter which one I give the twos. I could have labeled point B, x2, y2, and C, x1, y1. I would get the same distance as long as I plug them in accurately to my formula. x2, 4 minus x1, 6 squared, plus y2, -2 minus y1, +5 squared. Then we're doing parentheses. 4 minus 6 gives me -2. -2 minus 5 gives me -7. Now I'm squaring. -2 squared is 4, -7 squared is 49. And then when I add those together, I again get the square root of 53. So I've proven now that opposite sides are congruent. I'm just going to write my little answer in here. I've proved that opposite sides are congruent. Therefore, by my opposite sides, running out of room here, converse, this shape is indeed a parallelogram. Now, some of you might be saying, why would I use the distance formula? It seems like the other ways were quicker. And I agree, a slope formula and a midpoint formula are probably quicker to use than a distance formula. However, the challenge here is that parallelograms are not the only shapes we're going to have to prove on the coordinate plane. There's other four-sided shapes we're going to be learning about in this unit that have their own unique properties. And typically students do the best at identifying the differences between the shapes based off of how long the segments are in the figure, like how long the diagonals are, how long the sides are. In which case, figuring out how long stuff is with the distance formula is going to be your best bet of figuring out what type of shape it is. All right. However, it's your preference. If you like the distance formula the most, then you can remember, you can use it to prove that opposite sides are congruent, to say that a shape is a parallelogram. If you like the slope formula the most, you can prove that opposite sides are parallel to prove that that shape is a parallelogram. And if you like the midpoint formula the most, you can use it to prove that the diagonals bisect. They have the same midpoint to prove that your shape is a parallelogram. So if we're going purely based off of convenience, what takes the least amount of time, then I can figure out if this shape is a parallelogram with the midpoint formula. I think it's the quickest way to prove that a shape is a parallelogram. Again, we're going to have shapes where we're not asked to prove this is a parallelogram. We may have to prove that a shape is a rectangle. We may have to prove that a shape is a rhombus. All right, in which case, the midpoint formula would not be the most efficient way to figure it out. All right, so we'll learn that with time. For now, do whatever you're most comfortable with. Distance formula to prove opposite sides are congruent, slope formula to prove opposite sides are parallel, midpoint formula to prove diagonals bisect each other. For this one, we're asked to prove it's a parallelogram. I'm going to use the midpoint formula to prove it's a parallelogram, show that our diagonals cut each other in half. So here's one diagonal, KM. I'm going to be organized here. I'm going to say point K is at -3, +2. Point M is at +3, negative 2. I'm going to label them x1, y1, x2, y2, and I'm going to plug them into my midpoint formula. Negative 3 plus 3, that's x1 plus x2 over 2. And then we have y1, which is positive 2, plus y2, which is negative 2 over 2. And we see that we're going to get zeros here. Negative 3 plus 3 is 0 over 2. 2 plus negative 2 is 0 over 2. So my midpoint for this diagonal is at 0, 0. Okay, I'm going to write that up here. Just stay organized and keep everything on screen. Midpoint of KM is at 0, 0. Now we're going to do the same thing with the other diagonal, and if it has the same midpoint, then we know that our diagonals cut each other in half. So we're doing that with LN as well. Okay, point L is located at positive 4, positive 2. Point N is located at negative 4, negative 2. Got x1, y1, x2, y2. Again, plugging into our midpoint formula. x1, 4 plus x2, negative 4 over 2. y1, 2 plus y2, negative 2 over 2. 4 plus negative 4 is 0. 2 plus negative 2 is 0. And again, we get a midpoint of 0, 0. So we have the same midpoint, which means that our diagonals are cutting each other in half. So by the diagonals converse, we have proven that this shape is a parallelogram. So again, guys, it's your preference right now. If all we're doing is proving a shape is a parallelogram on a graph, we can use the midpoint formula to show the diagonals bisect. We can use the slope formula to show that opposite sides are parallel. We can use the distance formula to show that opposite sides are congruent. It's your choice for now. Later in the unit, it'll get a little bit more complex where a certain formula will work out better than another one. We'll see you when that time comes, guys.